This is Class Online. Kindly subscribe to my channel, like this video, make comment, share to your friend, and let them benefit of this video. Today we'll be looking at equation of motion under gravity. Remember in previous class we looked into equation of uniformly accelerated bodies, and I said in this class that we'll be looking at equation of motion under gravity. All right, let's proceed in our class. Now, what do we understand? What are we talking about when we say motion under gravity? Now, motion under gravity refers to the movement of an object whose vertical motion is affected by the presence of gravity. And the force that attracts object downward is gravity. If I throw any object upward, the object is going to come downward. So a vertical movement of objects is moving up, then coming down, is as a result of a force which is called the force of gravity, because the force of gravity pulls every object towards the center of the earth. Now, in fact, gravity works towards the center of the earth. The mass of the object and the gravitational constant determines the magnitude of the gravitational force. All right, let's recall something. Recall that W equals to mg, that is weight equals to mg, and weight is the force and is measured in Newton or kilogram, meter per second square, while mass is measured in kilogram, and gravity is measured in meter per second square. Actually, in previous classes, we've looked into the differences between mass and weight. So if you want to go back to that video, you can just go to the description link and look at the video where I talked about measurement, measurement of mass, weight, and time. So you can just go to that video and just look at the differences that I stated in that video between mass and weight. Now, for objects reasonably close to the Earth's surface, gravity is approximately as 9.8 meter per second square, but most of the time we give an approximate value to be 10 meter per second square. So in the absence of air resistance, like in a vacuum, because in a vacuum is a place that is void of air. So in a vacuum, all objects will fall to the ground at the same rate, regardless of their mass, shape, and size. Please get this concept right. If an object is thrown downward, irrespective of the size, irrespective of their mass, every object is going to fall at the same rate and at the same time. All right, this concept will be applied as we proceed. Now look at this. Look at when two objects are thrown, if they are hair, you see the feather will be blown, and therefore the mass of the ball, that green ball, will reach the ground faster than the feather because of the resistance of the air. But if we have a vacuum which is void of air, and we throw the feather and the ball at the same time, the two bodies is going to reach the ground at the same time. Well, this experiment was actually verified by Galileo Galilei. Remember, during the hold, we have the hold ideas that said that every object is going to reach the ground faster than the smaller object, or a bigger size object is going to reach the ground faster compared to the small size object. So that has been the whole idea before Galileo Galilei was able to discover that irrespective of the size of the bodies, every body is going to fall at the same rate, and this is due to the gravitational pull of the earth on the body. All right, let's look at this. Note that weight is different on other planets or celestial objects. The weight of an object is different. When you get to the moon, the weight of the object in the moon is not as the weight of an object on the earth. So let's consider the moon, for example. The moon is much more smaller in size than the earth, and the gravitational constant is approximately 1.62 meter per second square in the moon. So the gravity in the moon is 1.62. Is it very small there? Why the gravity close to the surface of the earth is 9.8 meter per second square. So as a result, objects weigh roughly 70% of what they do in the earth. If the mass of an object is 100 gram on the surface of the earth, is 100 Newton at the surface of the earth, when you take such object to the moon, it measured approximately 17 Newton. You see, 17 to 100. You see the margin. That's what we are talking about. Now, and this is why you often see the footage of astronauts slowly bouncing over the moon's surface, because gravity is less forceful and the astronauts are lighter there. If you see the astronaut, when they are on the surface of the moon, you see them bouncing on the surface because they are lighter. And because they are lighter, it is not convenient for them to walk freely. And that's why you see them bouncing on the surface of the moon. All right, let's look at this. Gravitational force. What we are trying to say is that when an object goes up, object must come down. Force that pulls object to the ground is what we call the gravitational force. And all things that have a mass, we have a gravitational force. As long as an object have a mass, it will experience gravitational force. Now, this force is weak when the object mass is very small. And I said when the mass is very small, the force is very, very weak. And gravity is not responsible for many of the movements that we experience in everyday life, except for things falling to the ground. So when we're talking about gravity, gravity is not responsible for all the motions. For instance, if I'm moving from Lagos to Abuja, gravity is not responsible for that kind of motion. But when we're talking about gravity, the motion gravity influences is talking about vertical motion. So when an object moves vertically, and that is when acceleration due to gravity have a part to play in such kind of a motion. All right, now let's look at this concept. Very, very important. So listen. Now we have two diagrams here. You see in the first diagram, an object is coming down. In the second chart, an object is thrown up. So please listen attentively. When an object is coming down, it is observed that the object is freely falling down. So the initial velocity of an object that is falling down is 0 meter per second because the object is coming from rest. It is freely coming down. Because it is coming down, the velocity at that starting point is 0. Why? When it hits the ground, the velocity is maximum when it hits the ground. Then the object cover the height h, as you are looking in the chart, and then g is positive. Why is it positive? Because the gravity is pointing downward and the object is also moving downward. So therefore, the gravity is positive. And time for this first chart, we call it t equals to t1. Then, let's look at the second chart. When the object is going up, object cannot go up without you throwing it up. So you need a velocity to throw an object up. And therefore, the initial velocity is maximum when you are throwing it up. So initial velocity is maximum at that level. But when you throw an object up, the object will keep going. And as it is going up, the velocity is reducing until it gets to a maximum height. So when it gets to a maximum height, when velocity is 0, then the object starts dropping and coming back. Then, which means at maximum height of any object you throw up, the velocity is 0 meter per second. Why gravity is negative as you throw the object up. And the time for this part, we call it T2. But it's very important to know that the time it takes an object to go up is also the same time it takes an object to come down to that same level. And that's why I said T1 is T2 equals to T2, because the same time you take this object to go down, we also take this object to go up. And therefore, if I ask you that when I throw an object up, what is the total time of flight? That is the total time spent by that ball in air is equals to the time it takes to go up and the time it takes to come down. So that is why the total time, capital T, equals to 2t. What I'm saying in essence is that if it takes 3 seconds for an object to reach a maximum height from a ground level, then it's going to take 3 seconds also for the object to come back to that same ground level. So please understand this concept. All right, let's go to the next slide. You can pause the video for the next slide to just master or to take note of those concepts. So that's the things you need to note. It's an important point you need to note. I've explained this important point, and that's what I previously explained, but I'm just giving you as a note, so you can just pause the video and copy that. So those are the important points. You can pause the video and copy that. All right, let's move. Motion under gravity. Let's recall. The previous class we have looked into equation of motion, uniformly accelerated bodies, which are given as V equals to U plus AT, S equals to UT plus half AT square, V square equals to U square plus 2AS, and the last one is S equals to half into bracket U plus T close bracket T. But now we want to look at equation of motion under gravity. Because the body is moving under gravity, we are still using the same equation of motion. But now, because we are dealing with a vertical movement, because it's a vertical movement, that is why it is equation under gravity. Then A, which is acceleration of body, is replaced with G, because the object is now falling under gravity. The object does not have its own accelerated body now, does not have its own acceleration now, but its acceleration depends on the gravitational force. So A is replaced with G. Then let's look at S. The distance S is now replaced with height because we are dealing with a vertical distance, and vertical distance is height. So if we substitute that parameters into the equation of uniformly accelerated motion, that we are going to have V equals to U plus or minus, instead of having AT, we have GT. Now, why do we have plus or minus? Because the motion under gravity is either in an upward direction or in a downward direction. When the object moves in an upward direction, we are going to use negative. That is, when an object is moved upward, we are going to say V equals to U minus GT. But when the object is coming down, we are going to use the formula as V equals to U plus GT. So the same way, it applies to the other formula. So here we say H, another formula is H equals to UT plus or minus half GT square. And the third formula is V square equals to U square plus or minus 2GH. Now, why is it that we are not using the last formula where we say S equals to half into bracket U plus V into bracket T? The reason why we are not using that formula for equation of motion under gravity is because that formula does not include acceleration. And when it does not include acceleration, then it is useless. We don't need it for those particular things we want to consider. All right, let's move to the next slide now. Let's go and just review the equation of motion once again under gravity. See, V equals to U plus or minus GT. Number 2, H equals to UT plus or minus half GT square. And number 3, V square equals to U square plus or minus 2GH. Okay, now let's apply the equations of motion under gravity in solving the following problems. Please make sure you sit tight, try to concentrate, like this video, subscribe to this channel, and turn on the notification bell so that next time I drop another video, you'll be able to see that video.